in 1993. I think, 1 minute. Armitage Medal in 1993 and Eccles Medal in recognition of his outstanding achievements in the development of logistics education in 1996 from Society of Logistics Engineers, SOLE in USA. In 1999, Dr. Nejovic formulated the concept of Mercy science, the body of knowledge for prediction of functionability performance of functionable systems type. Under his leadership, the Academy has educated thousands of professionals coming from industry, government, and military organizations worldwide. Some of them have received internationally recognized master or doctoral diplomas. With this brief introduction, I request Professor Nejovic to make his invited presentation.
Thank you.
Hello, sir.
Thank you.
Yes.
Right. Share the screen. Right.
Yes.
Yeah.
It is being seen, please.
Okay. So do you have? Oops. Okay. I'm sorry. Right. I didn't put the right. Do you see my slides?
Yes, we are able to see these slides.
Okay. Thank you. Well, good afternoon, ladies and gentlemen. It's a great pleasure to talk to you, although it will be much better if we are face to face, but between the two, this way is still better than nothing. I'd like to say hello to Dr. Warde, who is the chairman of the conference and the main pillar of the society, and all of you contributors, all of you in organizing committee. I enjoyed your presentation, your day today, and I'm looking forward for today and tomorrow. I got 30 minutes to share what I would like to say, and I'm grateful that I got open topic. So I decided to talk about military science approach to the Royal Reliability Challenge. Just for those who don't know, MIRCE is abbreviation for the management of in-service reliability, cost, and effectiveness. A few months prior to the royal visit, the royal visit to the gliding club has been informed that the king would like to be flown around the area to observe surrounding natural world. Well, the Royal Welcoming Committee asked the club chairman which particular glider of the existing 12 should be allocated to this royal flight, and should any additional maintenance be done to make the mission as safe as possible. You see, this is paraphrase the question which I asked a general about 35 years ago on reliability conference. And during the conference in front of 300 people, the general's reply was, which idiot asked that question? Well, it wasn't very pleasant to submit, it's me, but anyway, I did because I asked that question. So for this presentation, I changed it to the visit and the gliders, because really, that time I asked for the military aircraft, the current situation, it's not suitable for military, but extensive questions. We have 12 systems of the same type in service. What do we choose for the king to fly in the safe and reliable manner? The club chairman knew that the most reliable one should be selected, of course. But how do we do that when all of them are the same type, produced between 7 and 9 years ago, and flown approximately the same number of hours and such? So we are almost like siblings, like twins. During the in-service life, they have maintained in accordance to manufacturer's recommendations by the licensed engineers, and always the approved spare parts were used. So we have good example of very well looked fleet in accordance to all manufacturers and the design recommendations with qualified personnel. So in essence, this is my illustration. This is what the fleet look like. But we have 2 or 12 or 200 or 1,500 Boeing 747s are flying around the world. Well, from outside, from a manufacturer point of view, they all look the same. They have the same pattern of the club, etc., etc. So the chairman, just to take the story of the keynote speak, the chairman asked the glider manufacturer for help. Of course, the glider manufacturer says that is very important, and we use all our relevant reliability data, and they provided the data. So in typical reliability manner, there is a reliability block diagram, which I here am just sketching to 4 components just to have parallel series, just to illustrate. Of course, not that I'm teaching you what the reliability block diagram. You know that just to put things in the story. So we have reliability block diagram. We've done the study. We have now our classical reliability design in reliability function. So we have here reliability of the system is the probability that system will survive to the time t, and those components are connected in series and parallel, and that's what it is. And if we put some adequate information, purely this is for illustrative purpose, we will get some well-known reliability curve, and that is what we learn from initial beginning courses in reliability, but that is the fundamental of the last 50 years doing system reliability. Okay, so now we have a chairman of says, but what is the reliability? Well, the reliability engineer says, well, is the probability that the new system will not fail up to the stated time. Well, that's really start bothering now the club chairman, because he says, well, but none of my systems are new. They're all 7 to 9 years old. So what do I do? Well, that's really a good question. Because if we pick up any point on our reliability function, any point, if you look mathematically, is of the neutral nature. If you look at the from reliability point of view, then it is smiley face, because that face now tells me that the probability of not failing from here to here is whatever it is. But however, there is the other side of reliability, sorry, there is another side of reliability curve. So that is this area here. So what is that probability? Well, that probability is of very sad face, because this is the proportion of those who started at 0, which are not in service anymore. So now, if they are not in service anymore, what's happened with them? Where are they? What is this probability? How that probability applies to the real life, and what can we do about that to change it? Because really, what is the meaning of that? That's what I want to say for not new system. Okay. Oh, sorry. So the fundamental question is, where is, why is, I had a question mark. Anyway, where is maintenance? So in that screen now, we have good question. This is my reliability. As we know, area under reliability curve tell us mean time to failure, great. But what is this area here? And this curve now decreasing with time, but this area now is increasing and increasing. So where is the maintenance? Okay. Well, the main objective of this presentation is to introduce you, the audience, to, as reliability professionals, to the mutual science approach, which is based on the prediction of the real-time reliability based on the current in-service data of each individual system. So the reliability function, which I already shown you, is related to 1, 10, or 1,000 systems of that type. Now, after 5, 10, 15, or 50 years, each of them went through the sequence of events which make them individual. And now we don't have individual reliability function for 5 years old system with tail number so and so. So the recent developments of the new technology based on the digital transformation and the data connections enable the application of this method to the real life. So we had a theory, now it can work. Additionally, considerations regarding the execution of targeted maintenance tasks is justifiable, as the concept replacement just in case could have even negative consequences on in-service reliability of the system. So look, we have now two issues here. What is the reliability going to be in the future for existing system, 3 years old or 7? And for that particular one, is it beneficial to do some maintenance task? Because of course the royal visit is important. We want the maximum reliability. But what I'm trying to say here, that attitude or best practices sometimes used, or replace just in case because it's royal visit, in fact, for the certain components, for the certain failure mechanisms, could actually have a negative effect. So that is the point of the talk. So at age of 34, with all these academic degrees, I asked myself, is the crossing the finish line? Because that time, as students, I was rallying and racing. And in the racing, to be first you have to finish to cross the line. In the business, to make a profit, you have to deliver business plan. So is delivering business plan reliability question, which I got my master's degree in? Is it a maintenance question, which I got to do with through PhD because it wasn't enough reliability? Or is it my own question? Because you study one or the other. But how do you put things together? Because that 7 or 8, 9 years glider or 15 years old power station has many maintenance tasks already performed, new components. I mean, you can have the same car as your wife, but she's on the 3rd clutch and you're on the 2nd fuel pump. So which one do we choose for tonight to go to the opera, wherever you go? So that was a question which I asked many years ago. And in fact, that's the same time when I asked a question for the general, which aircraft should fly and should we do any maintenance tasks? But the rest of my professional life has been driven by the quest for the scientific answer to these self-imposed questions. See, this is what I wanted to know. Today, several decades later, and lots of gray hair, as you can see, I'm delighted to share the body of knowledge that provides my scientific answer to my question. Hopefully, it will be beneficial to other people, other businesses, and industries. Of course, that is the answer to the royal question, to the royal challenge. Well, I got only 30 minutes to expose what exists, not to tell you and teach you and you learn. So everything is described in the book, which is published by my academy in 2017. Any similarity between this lovely young boy and me is totally coincidental. And of course, lots of material from this book has been published in the book, which is facilitated and through your society, where Dr. Varde and Professor Prakash and Joshi were editors. Some of you remember, we all launched that book and got our copies 2019 in Chennai, where you are now. So if you are really, really interested what I'm talking about, well, either one book or go to chapter 23 of this book. So this is free advertising for Springer. And you can learn more what is miniature science all about. But as I will tell you now, in the nicest inspirational way, as a keynote who sets up the day, the spirit and atmosphere for the day, how it does apply to the Royal Challenge, basically. Okay, so fundamentals of miniature science. According to miniature science, at any instant of calendar time, any in-service system could be one of the following two states. Positive functionable states, a generic name for a state in which functionable system is doing the work. What is doing the work? Delivering a measurable function. Very simple. Delivering a measurable function. Commercial aircraft is a positive functionability state when it's flying 37,000 feet at 513 miles per hour, carrying 340 passengers and 100 tons of cargo. Negative states in one, which does not deliver function for whatever reason. Okay, so the axiom one of the miniature science says a system comes into existence in positive functionability stage 0. That's the birth of the system. So system is born. In order to exist, has to be born, and in order to fail, need to exist. So that is the axiom of the miniature science. In translation, just to put you briefly, in miniature science, functionability is the new word which I created in 1993. But in essence, it is addition, combination of reliability and maintenance. Reliability is design in characteristics of the system. Maintenance is in-service process, in-service property. So when we put together, we got functionability is the word which is new for some of you, but that is what it is. That's what I call it. Okay, so miniature functionability field is the new creation which enables system to exist through time. Okay, it is the set of functionability states, positive states for I-1 to infinity, and negative states for I to infinity. Okay, system is born in stage 0, and system finishes life at the negative states. Okay? So this is just illustrative example. So these are the functionability states on the vertical axis. This is the calendar time on horizontal axis. At every instant in time, you can find system in any of those states. So if you come here, for example, this is first, second, third, fourth positive state of the system in the 75 hours of operation. So now it has to be born, it was born, and then went to the negative state 1, 2, 3, etc. Okay, so this is the field within which system exists. Of course, probability, the union of all these greens give us the state of the system in the positive state, and the union of all red dots give us the event system is a negative state. Of course, there is a third axis, which is the probability which generates Mircea space, but we are not going to do that at the moment on this lecture. So that's the space. So a motion of in-service system through functionable state is governed by the following two types of actions. Negative functionability action that causes occurrences of negative functionability events at which systems are compelled to move to the negative states. So there are physical actions which compel the move. When I was doing this 20 years ago, for me, it was an analogy of Newton's mechanics. There is a force which generates the motion through time. Okay, so that in this case there is action, whether it's a corrosion or fatigue or bird strikes or tsunami, whatever it is. Once it's in negative state, system will stay in that state until it's compelled to move to the new state. Compelling motion from negative to positive state is related to maintenance. Maintenance actions, maintenance tasks, repairs, replacements, cleanings, adjustments, modifications, whatever they are, return the system to positive states. So, axiom 2 of Mircea science says, a system stays in the given state until compelled to change it by an imposed natural or human action. Tsunamis, corrosions, fatigues, and the rest are the natural actions. Human actions are schedule replacement, cleaning the filter, inspection of the power plant, whatever they are. So when power plant has annual inspection, it does not work. In some cases it does. When you change the oil in your car, the car doesn't work. So if you're a taxi driver and you are changing the oil, you're not making money. Your business is down, so you're in negative state. Okay. So what we needed now to find this motion, we are really now, we talk a lot about physics of failures. What I like to touch here is the physics of maintenance. Because see, reliability block diagram, it's not enough to tell me the states of the system. For example, those units B and C, which are in parallel, in one of the maintenance options, they could be sealed into one box, which is replaced after the failure of both. So systems are in parallel, the box works until system fails. So you see, yes, B and C within the box are in parallel, but from system point of view, system will fail when both of them fail. Okay? So this is now our reliability equation. You see, from maintenance point of view, due to maintenance and that design, now we don't have RB and RC in parallel anymore because we don't know when the first failed and the second. We only know when both of them fail. Is it BC or CB? We just don't know. So that's a different picture. Now, another option is units B and C are in the same box, but they are replaceable after the failure of each one, either B or C. But unfortunately, to do that, we disrupt in-service function. So that is the different curve. So now, yes, they are in parallel. And during the replacement of one, the second one is working. Now, there are many other options. Units B and C are totally in separate boxes. Yes, they are supporting system function in parallel, but they are totally in different boxes. And we can inspect the boxes and do different things. So what I'm really trying to say here, to address the royal question, which is addressing the reliability of the systems, which are not starting from the new. you can see my age and experience. From very, very beginning, I always challenge myself that reliability definition. Reliability is the probability that system will work for stated time. I always ask myself, but where is the origin of stated time? So if I look at my car, is it the stated time when I bought the car? Is it the stated time when I installed my last set of tires for the tires? Is it what is the stated time for my oil filter, for my brakes, etc., etc.? So what I'm trying to do here, to find the continuity of time, for me, for Mircea science, there is one time system goes into service in positive state at T0 when chairman, president, whoever comes to cut the ribbons for nuclear power station of the new school, that is time equals 0. What the pumps and the fuels and the chairs and the blackboards are doing with the school, it is within the school, but the time, that is the time 0. So when the chairman of the gliding club says, oh, my gliders are 7 to 9 years old, that's what I meant. That was my interpretation, of course, what he said. But they are 7 years from new. You see, if I like to know anything about you in audience, I just ask you one question. When you are born, and I know a lot about you. If I ask you a question, when did you have last curry, or when did you last time watch the film, I wouldn't know anything about you. Okay, so that is the point. In Mircea science, life has 0. So now I have totally different picture of I have my functionability field, which starts theoretically from 0, and we know the whole story, and life goes. But now, look at this. I can land, I can position now each individual glider within the fleet at Mircea functionability field. Here they are. So this one is here, is in positive state 4. This one is in positive state 2. There are 3 gliders here, 2 there, 5 there. So see, now we have time distributed, real time, calendar time, and functionability states. Now I know where individual gliders are, because I know this is in time, this is real time. Today, this glider is here. And if I look at the logbook for this one, I know precisely the path from 0, from new to that place, okay? And that is what I mean in real life. So, according to Mircea science, reliability of mission success. So now, the mission success for the gliding club and his chairman starts from the moment when the royal foot touches the gliders and goes in, and finishes when the gliders successfully land. That might be 20 minutes, 2 hours, or whatever it is. So I have now 12 gliders, 7 to 9 years old, just to make the story. Each of them could potentially fly the King for 2 hours. Which one do I choose and why? And do I do any maintenance? So now we have typical example of conditional probability. If, obviously, if any of these 12 gliders are not in operation, we wouldn't consider to offer the flight. So now we know positively that at the current time, they are reliable. They are in positive functionability state. So what we want, the time to failure happen after current time plus the time of royal visit. TR is the length of the royal mission. So we want the system to stay in a positive state from now until the end of the royal flight, given that now it's working. So that is conditional probability. And you see here, I've chosen the maintenance option purely for this case study, this keynote, to be where B and C are connected in one box. It could be any option possible, okay? That's what I said. So now I have a real picture of each glider, X-ray. I know the conditions. You see, if this one is the same box, I don't know that B has failed. So now why I'm talking about maintenance? Because I could do maybe some inspections here, or maybe not. Testability and everything else. So see, but what I want to say now, through time, systems are changing, personalities are changing, okay? And now, not that I only know that this is down, but this is down, it's the first failure. This component B here is second failure, okay? Whereas B is in the first operation. So you see what I'm now talking, I'm almost coming to the end, so don't worry, the chairman, Dr. Warde, I'm on time. So look, we are now looking inside. We are now understanding the gliders. So there are not 12 identical gliders anymore. See, none of them identical anymore. All that have the same stripes and the same tires and wheels and the brakes and the chairs and the ashtrays, etc., etc. But no, through time, they are changing. So my penultimate slide, purely for illustration, this is the probability of the Royal Mission success for existing gliders fleet. So don't worry, I just done this example for myself a few days ago just to show you something. So what we have here, 12 gliders, each of them are currently in the positive functionability state, but due to their histories, probability of being in that state are quite different. So now, based on this, the chairman of the club says, look, I will choose the glider number 1 because it's the highest probability. But now the question is, right, you choose number 1, would you do anything to improve it? Now it's interesting. Now I'm going to shock you, but please don't get upset. What this graph says here, if I go now and hypothetically, this is purely now my mathematics working. If I do changes of all others, just in case, you remember what I said? So look, unquestionably 1 is 0.92. So now that 1, which was black block here, it's not the highest. So if I do any maintenance tasks of the rest, I will notice now that due to the royal visit and the highest reliability is if I chose glider 9 and to the chose 9, the glider 9, I have to change components B and C. So that's the total point. So now, I hope you understood the narrative. Ignore this. If you want to learn it, we can learn it happily. It is simple and easy once you understood the philosophy. Once you understood there is a life of each glide. So my time is coming. What I want to say that the last graph clearly illustrates the potential advantages of using Mircea science approach to the real-time management of individual systems that will deliver reliability, safety, and sustainability of the fleet considered. So now, every morning Air Indigo fleet in Chennai, out of 50, 60 Airbuses or 737s, you know precisely which one is the most reliable because you have the mechanism to do it, okay? So with this, I finish. I wish you all success for the conference today. And I sincerely, sincerely hope that we'll meet in person on the next one, whether it's a year or 2. So thank you for inviting me. thank you for opportunity to share my knowledge with you, and I'm happy to answer any questions if there are. Thank you.
Thank you, Professor Javik. It was a very lively presentation, and I'm sure all the participants got how to use this reliability concept in the field in order to make the decisions in real time. So this is a very important talk, and I'm sure that if any participant, if anybody is having any doubts or any questions, they can ask Professor Jasdomir Nijovic. The question answer hour, basically these particular question answers will be for about 10 minutes, starting from now. Hello?
Hello?
Hello, anybody can ask doubts to Professor. Are there any queries? Are there any questions?
They are confused, you see, because...
No, sir. So, Professor, your presentation was very, very clear. Like, it was very simple so that we could understand each and every slide. Okay. Have you tried on fuzzy reliability aspects? Could you show can you throw some light on this?
Sorry, can I throw some light on what?
Fuzzy reliability, sir. Fuzzy reliability aspects.
Facility.
Fuzzy reliability.
Fuzzy set.
Fuzzy reliability.
Application of fuzzy sets.
Application. Yeah. Well, you see, everything is what I tried to say in the presentation. For us, reliability for definition, for me, that huge problem was the question for stated time. So the application really is to look at the system and start monitoring. You know, nowadays people, I didn't want to mention that because I'm not absolutely sure yet whether Industry 4.0 works. And see, there are lots of names and the new words in the technology. We are talking about digital twin. We are talking about Industry 4.0, maintenance 4.0. But basically, what the world is moving now to try to monitor, to have a census, to know exactly what are the age and the condition of the system. So if you look to identical, I don't know, cars, Suzuki Swift, which are popular in India, both cover 77,000 kilometers or miles. If you look at their logbook, each of them is different. They have different pump, different tires, different brakes. So if you to choose one to take your friend to hospital or to go to the wedding, you will be able to do it. See what I'm now saying, that 67,000 mile Suzuki Swift are not the same. They're all different. After 67,000 miles, which is say 3 years in service, they're all different. When they were identical at the Suzuki company in Japan, while they are designed, there is one set of technical drawings, there is one reliability function, there is one MTBF for every component. But now, in reality, each of 100,000 of them on the street, they're all different. And that's what I'm trying to capture. I'm trying to understand in service. You see, design in reliability, we've done it. But what about in service reliability? That's what I'm looking. And that is what the presentation is all about.
Okay. Thank you, sir.
I hope I haven't confused you more.
No, sir, not at all.
Hey, it's fine, sir.
Yeah, I mean, Dr. Varde and Professor Prakash, they have my email address. Look, I love what I do. I like working with Indian people there and stressors. So please, if you have a question in 3 hours or 3 days or 3 months, just send me email. I'm happy to collaborate.
Thank you, sir.
Thank you, please. If anybody is having any questions, any participant having any questions? Okay. If there are no questions, Professor, I have a question. I have one doubt actually. It is not a question. I have a doubt. basically, when we are trying to talk about the maintained systems, now how to incorporate the efficiency of repair or the maintenance in the reliability prediction?
Oh, what a beautiful question. Ah, it's a so beautiful question. I've done lots of work on that. And of course, in 30 minutes today, I didn't have time even to mention that. Absolutely beautiful question. And it is so important for miniature science. As I said, the classical reliability starts from zero. But when we replace the pump for the first time, that pump now has inherent reliability characteristics and the failure mechanisms which act on it. Plus, we have potential of all maintenance-induced failures.
Yes.
We have potential for all failures which happened when the pump was sitting on the shelf, and we have rats and mice and the rain and the -50 temperature, etc., etc. So yes, in miniature science, we are incorporating all additional maintenance mechanisms which impact the reliability of subsequent operation, not new anymore, of the subsequent operation. So one of the big work which I've done for Airbus on Airbus A380 about 15 years ago, when reliability people who deal with the pumps or landing gear, they says, oh, I've flown 2 million miles and I have 67 pumps fail. No. Out of these 67 pumps, 30 failed first time. Some of them failed second time. Some of the pumps are modified and put in service already modified. So no, you don't have, you call them part number this and this, and they're all yellow with the green dot, but they are not the same. You have to allow us to take maintenance-induced failures, operational, shelf life, transport, packaging, storage, and everything else. So thank you for the question.
Thank you
It's
very
huge.
much. Thank you.
And I like to continue talking with you, but I know you have a time schedule.
Thank you. Sure. Thank you so much, Professor. Any more queries? Any more queries? It was an excellent presentation. If no more queries are there, I think I will say that thank you very much to the professor. It was an excellent presentation because we could understand many of the participants did not ask the doubts because they have understood what you have presented, especially the. Yes,
I know,
yes.
but that is good. They either understood or they are shocked, but both we make objective, because for me, keynote is to motivate, inspire, and confuse sometimes.
Yes. Thank you
very much.
Professor.
All the very best.
Thank you, sir.
Thank you.
Thank you.
Bye-bye.
Madam?
Yes, sir.
So it is up to you, madam. Over
Yes.
to you.
So now, okay. After such a motivating speech by our professor, so we are going to start our technical presentation sessions. So breakout rooms have already been created. So I request the participants who are going to make the presentations in technical session 6 to kindly move to the room.
Probably you can mention the title also. Technical session 5 on live prediction and prognostics can remain in this room.
Yes.
And technical session 6, fuzzy and digital system reliability, can move to the technical session breakout room.
Yeah. Abstract number 824. By 824, network reliability of cluster-based ad hoc network using fuzzy graph, Sriram. Then 825, 831, A35 and A58. I kindly request the authors to move to the breakout room. And authors of the abstracts number A11, A13, A23, A34 and A04 kindly remain in the Zoom main room itself.
I think technical session 5, Dr. Muthukumar is the chairman.
Yes, sir. Yes, sir.
Yes, sir. He has already come, sir.
Yeah, I am available, sir. Yes, sir.
Okay, somebody has to introduce Dr. Muthukumar.
Yes, sir. Yes, sir. I will be doing the introduction. So once again, I'm just checking about the technical session 6. Like,
Okay.
there already Dr. Velmurugan sir has gone over there. Shaili Vardhe has gone, but the remaining authors.
Yeah, I see almost 4 authors already present for technical session 5 in the main room. They're
Yes.
logged in.
Yes,
But
sir.
technical session 6, I could not see.
Yes, sir. No one has.
Can we request if the participant is there to say hi and then move to the other room?
Sure, sir. Yes, Anandi.
No, we can go from the beginning. Mr. K. Sriram, is he there? A24.
Once again, sir.
And G.
Sri-
Kupusamy,
G.
A25.
Kupusamy is not there. Sriram is also not there, sir.
A31, that is Sharmila.
She is not there.
Okay, and A35 is Anandi, Vaishnavi and Anandi. Are they available?
Anandi also right now not available, sir. Like Sharmila, she won't be able to present. She has met with an accident, so Sharmila will not be able to present.
Okay.
Let me confirm with others. Bhupati said he will be joining.
Bhupati is the only person left in that room otherwise.
Yes, sir.
Has he joined? I couldn't see him also.
He has also not joined yet, sir.
If that is
Sir,
the case,
Ah.
We can look at this, what is there in the main room. If one of the papers is not there, then we will accommodate.
Yes, yeah, that also here. We'll not have the parallel session.
Yes.
We can accommodate everybody in technical session 5 itself.
Provided there is one more author is not there in this. We have to see that. All of them have come in, then we have to give them the time.
One second, sir.
Yeah.
Sir.
Should we check out in the main room also?
Yes, sir. Yes, sir. Ahmad.
Ahmad would have come, madam.
Ahmad has come. Then Vishnuvardhan.
Yes, yes.
All are there except A23, Nishta Shreya.
Except Shreya.
Okay. All other 4 are there. I checked that.
Sir, then shall we?
I think we can start the technical session 5 live prediction and prognostics. And as we go on, we'll see if the other author joins. We can put him here itself.
Yes.
Then can we ask Dr. Velmurugan sir to come to the main room so that they can jointly?
Correct.
Yes.
Yeah.
Shall I ring him up, or I think
no. I will move him, sir.
Okay.
Yeah. You can move. Only 3 are there now. Only 3 are there in the other session. You can move.
That's what I have asked him to move to the main session.
Okay.
Yeah.
I think has he moved? Velmurugan sir, நீங்களும் main session கே வந்துருங்க. Yes, please ask him to come to the. Sir.
Shall I ask him, madam?
No. We have already informed, sir.
Okay. Thank you.
We have informed through the meeting itself.
I think the session can start.
Yes, sir. We can start the session, sir.
We can next
Okay.
Dr. Muthukumar sir, introduce பண்ணுங்க.
Yes, sir. I will. Okay. So sorry for the confusion. Okay. So the chairperson of this technical session is Dr. R. Muthukumar. So welcome, sir. So he is at present the director for the Center of Reliability STQC Directorate at Chennai. So he has a vast experience, that is more than 3 decades of experience in the field of reliability engineering. So he has a lot of certifications, like he is a certified reliability engineer, information and security system auditor. So he is a quality system auditor. He has a certified proficiency in accelerated live testing and reliability engineering, etc. So he has received a number of awards. To mention an important one, so he has received the certificate of honor from his department for being the project leader for successfully completing the project qualification of mini charge amplifiers SMT technology as per the European Space Agency specifications for the space applications of VSSC ISRO Trivandrum. He has handled a number of reliability projects. There is a sonar system for NPOL Cochin, onboard computer systems for AWACS, and ALTAS project for Indian Navy, axle counter system ACD IPS for Indian Railways, and so on. So he has contributed to more than 55 technical papers on reliability engineering. He is a lead trainer in the national level certified reliability professional training program, and he is also a lead faculty for failure analysis reporting and corrective action training program. And he is in the syllabus committee of various universities. He has guided a number of students in the field of reliability. So this is really very, very shortened profile. His laurels are moving to pages. Now I request Professor Muthukumar to kindly take over the session.
Yes, madam. Good afternoon, everybody. Thank you very much, madam, for the nice introduction. I think we are having all the presenters here. The first paper, actually, we are supposed to start around 3:50. Of course, now lately it is going to be 4. I think around 4 it is. So, shall I call upon Mr. Gaisuddin Ahmad and P. Kamachi to present the first paper?
Hello.
Yes.
Am I audible, sir?
Yeah, you are audible. Please.
Okay. Thank you.
Yeah, continue with your presentation, sir, please.
Yeah.
Actually, each paper, I think the time allotted is 10 minutes. So I think within this 10 minutes, we should be able to give some opportunity to the participants also for some questions. So please try to, quickly come to the, your point, what you want to, what is your research and all. Okay, sir?
Yes, sir. Yes, sir. Sir, is it visible, sir?
Yes, yes.
Right.
Slides are visible. Yeah.
Fine, sir. Good afternoon, sir. Today I'm going to present about the statistical characterization of service life of corroded base years. Actually, this is our today outlines for the presentation. So as we have already seen so many bases, in this picture also we can see here that that this bridge has been damaged due to the corrosion, and here also we can see that spanning of this cover concrete has happened due to the corrosion. So as we know that bridge are the most important infrastructure for the Indian transportation system. So but due to corrosion it degraded. So due to the degradation, the capacity of bridge structure will get reduced, and with the reduction in that capacity, the service life will also get reduced. So as we can see that corrosion, whatever the corrosion is induced in the concrete, that is due to ingress of chloride or carbonate or sulfate. That are the main source of corrosion. So in this present paper, I'm going to discuss about that service life for this bridge piers subjected to the corrosion before the spalling of cover concrete. So here are some of the deterministic models are available in the literature. If we see that service life of structure, so as we can see that service life of a structure, various models are available. But if we talk about this service life, so Tuti's equations are Tuti's models are most and widely accepted among the researchers. So according to the to this um, service life model, we can see here that corrosion initiation period and that propagation period. So we can see that service life equal to initial corrosion initiation period, that is T initial, and after that T propagation, that is TP. So here we can see that that service life is basically depend upon the corrosion initiation time and corrosion propagation time. But we have modified here that if we see the modification of this service life model, so service life model can be modified, and it actually we have modified that corrosion propagation time into two parts. Like first part is that time of corrosion before the first crack, and after that before the spalling of cover concrete. So here we can see that now in this diagram we can see here that the situation is there T initial plus, after that this is the T crack, and after that T spalling. So this how what it is not like limited to T spalling. After the cover spalling of the cover concrete, it can take load further. It can take load, but here we are going to study up to TSP, that means spalling of cover concrete. So after the spalling of cover concrete, we need to go for the repairing. So corrosion initiation time basically depend upon basically corrosion initiation time is basically that once chloride reaches the surface of this corrosion, surface of rebars, then corrosion initiate. So that time taken for the to initiate the corrosion process is basically called corrosion initiation time. So corrosion initiation time that depend upon the diffusion of chloride into the cover concrete. So that diffusion of chloride can be modeled using the fixed second law. So that how we can model the corrosion initiation time. And after that, the diffusion coefficient, whatever earlier we have shown that T initial depend upon this. So here we can show that diffusion coefficient, basically the diffusion coefficient depend upon the water cement ratio, curing rate, and environmental exposure condition, as well as material properties. So we are going to so here we can see that in that literatures we can see that that model has been defined by Castaneda, that we can see that diffusion coefficient how they are modeled, and with that we they have modified this corrosion initiation time that we are going to use for this to calculate the corrosion initiation time. So after that corrosion initiation time, we have to calculate the time after the initiation of corrosion. So once that corrosion is started, volumetric expansion will start. So that volumetric expansion will be due to the rusting of rebars. So once volumetric expansion will be there, then hoop stress will induce in the concrete. So if hoop stress is greater than the tensile stress of concrete, then first crack occurs. So for modeling the first crack, we have one models for the mad body and models in there. With that, we can use calculate this time for the first crack. Now we can see that once crack has been formed, so once crack has been formed, then it will elongate. So it started the propagation. So volumetric expansion is keep on going and rusting take place. So crack propagate. So once crack width is going to be more than 1 mm, as from the literature we can see. So once it is going to be more than 1 mm, we can see that spalling of cover concrete has happened. So if crack width will be more than 1 meter, that is leading to the spalling of cover concrete. So that TSP, that's called TSP. So that time we can calculate by using this model. So now we have taken the case study for calculating the service life of this structure. So this is the typical structure that is situated in the Chennai that I have taken for the consider for this calculation. Now statistical modeling I have did for the 9 cases. So 9 cases are basically from the depend upon the water cement ratio and curing gauge. So this how we have tried to model this initial and these are the random variables we have chosen from the literatures for calculating the T initial. And for different times, we have calculated this means and standard deviation for different cases. So we have taken 9 cases, and for all 9 cases we have taken. So, and four severity condition we have considered here, like mild condition, moderate condition, severe and extreme severe condition. So we can see that corrosion initiation times for the mild condition is like more as compared to the extreme condition. So in this way, it depend upon the like water intensity also and curing time also. For case one, suppose we have seen that case one. So for this case, if I have taken this corrosion initiation time, so we can see here that how corrosion initiation time is going to affect for the different exposure condition, like mild case, moderate case, and severe case for extreme case. And after that, we have checked for this distribution. So we have checked the distribution, and it is like log normal CDF is correctly fitting with this CDF. So same way we have calculated also TCR and TSP. So TCR, TSP we have calculated with the these parameters are there. So with this parameter I have calculated TCR, and for that we have seen that here what is there, here normals and log normals both distribution are correctly fitting and satisfy the goodness of it hypothesis test. So that we have did here also we have did this hypothesis test, and we have checked that both log normal and normal distribution are fitting. After that, we have find out we have added this T initial and T propagation that we have added, and after that we have checked that service life of this structure. So we have got for the mild case, we have got that 57.55 with the mean, and standard deviation is 33.404. So in this way, it is just behaving like a mild case, moderate case, severe case, and then extreme severe case. Now in this paper, actually we have generally we have like model this uncertainty for the RCD structure, like we have identified the random variables from the literature, and we have calculated the corrosion initiation time and time for the first flag due to corrosion, and propagation time we have checked. After that, we have calculated we have estimated the service life for different for the condition like mild, moderate, and severe condition. We have after that we have fitted this log normal distribution, and we have found that it is passing that chi-square test for 95% of confidence level, and then we can say that this procedure can be demonstrated can be adopted for the other structure also, like we have did for the peers, so that we can do for the other critical structure also. That we want to thank that Director CRC for granting me to publish these papers, and also I want to thank Dr. J. Prakash sir and other technical staff of Star Laboratory. Thank you.
Thank you, Mr. Ahmed. I think nice question. We have also been within the time limits. Now it is 4:11. So I think it's a nice presentation on the progression of the corrosion. Right from the corrosion initiation point to the corrosion development, and finally the crack development, and finally using statistical methods, we have arrived at the service life of the numbers. It's very good presentation. So now the session is open for the participants, any of the participants, to throw a few questions to Mr. Ahmed. I think he'll be pleased to answer the questions on his research. Over to the audience, please. Participants are requested to ask some clarifications or questions to the presenting author. He has completed his presentation. I request now the participants to throw some questions. I think if no questions are there, can I ask one question, Mr. Ahmed?
Yes, sir. Yes, sir. Sure.
Yeah. Actually, you have assumed a chi-square distribution at 95% confidence level. 95% confidence level, what exactly it means? And when you take 95% confidence level, the risk factor is 5%. What are the risk factors? And, I think, yeah, just I will complete my question. And you have considered mild environmental exposure, moderate, and severe and extreme. So how do you categorize this? So can you please?
Yeah. Yes. Sir. Sir, these are the conditions for the mild, moderate, and severe condition. So we have surface chloride concentration. So for different exposure condition, we have different surface chloride concentration. Based on that, we have categorized mild, moderate, and severe, and extreme severe conditions, sir. And
I understand, but how do you define a mild, moderate? Is it the level of what is the pollutants, or what is the condition? You are not specified what is a mild condition and moderate condition.
sorry, sir.
Is it okay? You could understand now what I am asking?
Yeah, yes, sir. I'm sorry, sir, that I don't know
Okay.
about much.
Okay, fine. Okay, and about the confidence interval, confidence level?
Yes, sir. Confidence level, we have for that this like 5% risk factor. We have like chi-square test tables is there. So we have did the chi-square test for this observed CDF and our like log normal CDF. So we have two CDF is there. What we have did, we have just taken that difference of this, and we have taken that as part of that. And after that, we have summarized all those things, and we have checked that whether this is fitting with this. We have tables is there. With that tables, we have checked whether it is passing with whatever the percentage is, it is passing.
Okay. Okay, good. Nice. Thank you. Thank you very much.
Thank you, sir.
I have a question. Can I ask?
Yes, please.
Yeah, in the last but one slide, you had showed the service life. Yeah, previous one.
Yes,
Here. See, the mean value is 57 and sigma is 33.4. With such a large variation, and the maximum minimum is also very, you see a large difference.
Yes,
So
sir.
what is the sample size you used?
10,000, sir. 10,000.
10,000.
Yes, sir.
So with this amount of large variation, how do you justify your result? Mild especially.
Yes, sir. That large is there because we have different different distribution function is there, sir. So for different distribution functions, suppose we have only we have normal distribution function, then we can get means will be like in that range, and sigma will be less. But we have a different distribution function. So for different distribution function, that can happen, sir.
But then what is the justification of the selection of distribution? So if you say it depends on the distribution, there should be some basis for selecting a particular distribution.
So as far as the input parameter is concerned, that whatever is suggested in the literature, that has been taken for the chosen random variable, sir. This is one of the author, Kamakshi.
Yeah.
So whatever input parameters that have been chosen, the suggested distribution functions and COV values that are prescribed in the literature has been chosen, sir. Those based on those guidelines, the sample has been generated.
Okay.
Yes, sir. But as you rightly said, it is a huge variation is there. But the mean value,
that is a query because
yes,
because the sigma is so high and very closer to the mean. So how do you statistically it doesn't justify?
That is but this doesn't. I don't know whether I can tell. But case test, there is a problem in getting the case test passed for this 95% confidence. So only this chi-square test has been done. So
yes, sir. Sir, if we go, if we have if we see that further initiation time that has been, if we can show you here, sir, that here we can see that for this mild and this. So with this already it has been like huge variation is there, and that also one paper is there literature in that we can say that they are also they have reported in the same day that this like means and standard deviations are like huge variation will be there.
Okay, thank you. We'll
Thank you,
discuss more later.
Thank you.
Yeah.
Thank you, Mr. Ahmed.
Thank you, sir.
Yeah, thank you very much. So, madam, can we call upon the next presenter? Yeah. Mr. Vishnu Vardhan is available.
Yes, sir. Good evening, sir.
Yeah, good evening. Good evening, Mr. Vishnu Vardhan. I think he will be presenting on crack growth life prediction in API 5L X46 grade steel pipes subjected to cyclic internal pressure. Okay, please continue. You will have another 10 minutes for presentation, followed by maybe few minutes for question answer. Okay, thank you.
Thank you, sir. Good evening, everyone. I hope the slides are visible and I am audible. Yeah. The paper is on,
your slides are visible. Yes, yes.
The paper is on crack growth life prediction in API 5L X46 grade steel pipe subjected to cyclic internal pressure. I'm Vishnu Vardhan from Structural Engineering Research Center, working in the area of fatigue and fracture. So as we know, the piping systems for transporting oil and gas and also petroleum products are essential infrastructure that plays a vital role in nation's economy. And these piping systems are one of the safest modes for transporting oil and gas because the frequency of accidents are less. But nevertheless, the piping systems deteriorate with age, and hence the periodic inspection and maintenance of these piping systems are essential. And once the failure happens, the consequences are high because of loss of life and also the property. And if you see on the right side, so we have a pie chart where the different types of failures are reported in terms of percentage. So, for example, natural calamity 6%, and the failure due to corrosion and pipeline rupture are about 20%. So, this study is mainly related to this corrosion and pipeline rupture failure. So, if you see the major causes of pipeline failure, there could be either due to external interference or the corrosion or metal loss. And external interference is mainly due to impact of foreign objects on the pipeline, mainly by the third party activities. And in the case of onshore pipeline, it could be due to excavation for development of projects such as roads, railways, and construction projects. And in the case of offshore pipelines, it is reported that it is mainly because of the impact of shipwreck anchors or other underwater foreign objects. On the bottom, we have figures where the different types of defects are shown in the case of first one. So we have dents, we have loss of coating, and what is known as gouge, which is basically a metal loss on the surface over a larger area. And these are due to external interferences in the onshore pipeline. Similarly, in the offshore, we have either it could be, you can see there is a figure with the dent and rupture as one of the failure mode. And of course, on the we also have long seam cracks, long seam cracks in the weld portion as well as on the pipes. And if you take the types of defects on these pipelines, one is due to corrosion. It could be either the sweep corrosion or sour corrosion. And the next one is the gouging, which I have already mentioned, or it could be due to the other defect is a wrinkle. Or we also have cracks, different cracks are mentioned here as per API classification. It could be either surface crack or a through wall crack or an embedded crack or a corner crack. And the other defect is a dent is another defect, and it could be a combination of any of these defects in the pipeline. So that could cause failure. And some of the previous studies are summarized in this, and the researchers have tried to study the fatigue damage and life through different approaches. For example, strain energy approach and parameters like fatigue damage parameter. And also reliability studies have also been carried out to estimate the probability of pipe failure due to wall thinning caused by internal corrosion using the Monte Carlo simulation. And in the present study, what we have done is we have carried out experimental studies on two pipes which are cut removed from the in-service pipeline, which was in service from 1985. So one pipe contained a longitudinal seam crack, the other pipe contained what is known as a lamination defect. So these are the pipe dimensions, 4 meter length, and the outer diameter is 14 inches, approximately 355.6 mm, and 7.14 mm thick. And the grade of steel is API 5L X46. So these are the metal properties. So these defects have been detected using what is known as intelligent pigging method. So it is basically an inspection technique where inspection probe called a smart pig is propelled through the pipeline and mainly to detect material loss due to corrosion and other defects. So these defects, the lamination defect and the crack have been detected using this intelligent pigging in the service pipeline. And you can see on the right side the longitudinal seam crack picture. So in the present case, in one of the pipes, as I already mentioned, the longitudinal seam crack is of a length 32 mm and a depth of 2 mm. And the other pipe contained lamination defects. There were 2 defects of different dimensions, which are mentioned below. So it's basically a separation of material in the thickness. So the pipes have been instrumented with strain gauges, 2-element rosette strain gauges. One set on the location where there was no defect, and one set of strain gauges close to the defects, both in the case of pipe containing longitudinal seam and in the case of pipe containing lamination defects. And there is no standard test procedure for this, so we have come out with a test procedure wherein we have used. So this is the pipe on the right side, and both the ends are welded with blind flanges, curved blind flanges. And the pipe contained 2 openings to fill the pipe with hydraulic oil and also to monitor the pressure. And the pipe was filled with hydraulic oil, and then we also devised what is known as a slave cylinder, which was used to pressurize the pipe through an universal testing machine. And this is the pressure cycle which was followed, and this is the typical pressure cycle which can happen, which is reported, which happens in a typical Indian oil pipeline. So with a pressure of 5 kg per centimeter square to a maximum of 77 kg per centimeter square. So this is the pressure cycle which was followed, and just 1 cycle per minute at the rate of 1 cycle per minute. And as I already mentioned, we have used strain gauges at different locations. We can see here the strain response with respect to time at different cycles. So as we can observe, the strain gauges located close to the defects have shown rapid increase in strain before the occurrence of through wall crack. So that is failure. And similarly, in the bottom, we have a strain response with respect to pressure. So we can also see here the rapid increase in strain towards the failure of the pipe. Similarly, these for the strain response for the other specimen with the lamination defects. So here also we are able to detect the failure of pipe through the strain response. And this similarly at other cycles. And we've also, these are the failure of specimens. This is what with the first pipe with longitudinal seam. You can see here a appearance of a through wall crack at the defect location. So the failure happened at 1,412 cycles, which represents approximately 3.87 years of remaining life. And similarly, failure on the other pipe happened at 2010 cycles, representing a failure of remaining life of 5.51 years at the rate of 1 cycle in a day in the actual pipeline. And we've also carried out numerical studies using finite element software with the dimensions of pipe similar to the dimensions used in the actual experiment, and also with the same dimensions of notch configuration. So these are typical stress distribution in the pipe. So the location of the crack was at the actual location of the pipe which was used in the experiment. So we have calculated, we have evaluated stress intensity factor, which is basically the parameter which represents the state of stress at vicinity of crack. So once you are able to evaluate stress intensity factor, the crack growth rate and hence the fatigue life can be estimated using the available models. And we can also see here the stress intensity factor with respect to the first figure is with respect to increase in crack depth, and in the right side with respect to these are the SIF for the crack tips in the surface. And we also have predicted stress intensity factor using the expressions given in two different standards. One is API code, the other one is ASME boiler and pressure vessel code. So we have used these expressions for calculating stress intensity factor, both at surface point of the defect and also at the deepest point for different crack lengths and also for different crack depths. So as can be observed, the SIF values predicted using ASME expressions given in ASME code were always higher when compared with the SIF values predicted using API standard. So once we have the stress intensity factor values, the one simple model relating crack growth rate and stress intensity factor range is Paris crack growth model. And we have used the crack growth constants, C and M given in literature. So these are the values used. And using the SIF range values, we could try to predict the life using the SIF values obtained analytically. And we can see here the comparison of number of cycles predicted. These for the case with this longitudinal scene. So these are the number of cycles predicted using experiments, and these are the value experiment number of cycles predicted using API standard and using ASME code of practice. So the values predicted using API code, the value predicted using API code is much higher, and whereas ASME would be able to predict close to the experimental values. So to summarize, fatigue life studies have been carried out on this API 5L46 grade pipes containing different defects, and the remaining life has been predicted for these two pipes representing 3.87 years and 5.51 years. Numerical studies were also carried out on the pipes under cyclic internal pressure, and the stress intensity factor values were evaluated by varying crack length and crack depth. And SIF values were also predicted using two different equations given in two different codes of practice, and using the Paris crack growth model and the crack growth constants reported in literature, the number of cycles to failure have been predicted for the API 5L X46 grade pipe. Thank you.
Yeah, thank you, Mr. Vishnuvardhan, for the nice presentation. I think it was really a very good presentation, and, with a lot of experimental data. I think you have conducted a pressure cycling test, and based on the crack development, you have predicted the future crack migration. It's okay. It's fine.
Yes, sir.
Yeah. Okay. Thank you for the nice presentation. Now it's time for the participants to seek any clarifications or further points on the topic presented by Mr. Vishnuvardhan. Over to the participants, please. Participants? I think
could you also analyze the combined effects in your analysis?
No, sir. Not in this, sir. No, sir. No. We have not considered the combined effects.
Okay, thank you.
Any other participants wish to seek some clarifications or doubts, questions? I think if no further questions are there, I think thank you very much. It's a very nice presentation. Only thing is, I just wanted only one question from me. Why there is a difference? Could you analyze the difference between the ASME and ASME BP and PV code?
Yes, sir. One reason could be the crack growth constants, the C and M values which are used, are basically evaluated basically for inert environment. Whereas these pipes, which they experience also corrosion, so that could be one reason. And the other reason could be, as I already mentioned, these pipes were already in service from 1985. So they're almost in service for 30 years. So probably that effect is not considered in this numerical, in the analytical expressions. So that is another reason.
Okay. Thank you very much. Thank you. I think participants, if you are happy with this presentation, we can give a round of applause to. Thank you. Okay. Thank you, Mr. Vishnuvardhan.
Thank you, sir. Thank you.
So we'll move on to the next presenter.
Bhupati, please wait. Third will announce.
Yeah. So the next paper, A23 participants are available, presenters are available, madam. Nishtha Shreya and NS Joshi. Are they available?
Shreya,
Nishtha Shreya and NS Joshi. Prognostics of aluminum electrolytic capacitors in DC-DC converters.
I could not see that. I
Oh.
could not see that author, A23.
Oh.
Bhupati, can you stop sharing your screen, please?
Yes, yes. I think his screen is visible, sir, already.
அதான் சார் ஸ்டாப் பண்ண நான் ஃபோர்ஸ்ஃபுல்லா ஷேர் பண்ண சார். I will stop the sharing.
Okay.
Okay, then now it is on fuzzy multivariate polynomial fitting. I think Dr. Velmurugan will be sharing this. Velmurugan?
Yes, sir.
Yeah, he's available. Yes.
So what about other papers in your session?
No, I think now I think Mr. Bhupati is ready to present, so let him continue.
Yes.
Both are combined now. Both are combined. Yes.
Yes, sir.
Okay. Shall we?
Can I start?
So what's the plan now? Shall we start?
Yes. I think, Madam.
Yes, sir.
Madam,
Please.
who is going to introduce Dr. Velmurugan?
Once again, sir.
Yes.
Velmurugan, can you please introduce Dr. Velmurugan to the audience?
Yeah, Mr. Bhupati, please wait for a few minutes, please.
Hello.
Can I start?
Ma'am, is my voice audible?
Yes, please.
Yes. So,
Dr. S. Velmurugan is currently working as the Scientist D as well as Joint Director in the Center for Reliability, STQC, Directorate, Ministry of Electronics and IT, Government of India. Dr. S. Velmurugan has completed his BE ECE with distinction from Anna University, Chennai. He did his MS in Software Reliability Engineering in Anna University. He did his PhD in Computer Science Engineering from Pondicherry University. Sir has delivered many lectures in the area of ethical hacking, reliability engineering, cybersecurity, etc. as a special invitee to engineering colleges as well as in universities all over India. Also, he has participated in many technical talks in various conferences in India and abroad. Sir has published numerous papers in national and international journals and conferences. To his credit, he has proposed 2 patents in the area of software development lifecycle. He has published a book entitled Software Reliability Determination Model by Lambert Academic Publishers. Also, he is the lead faculty in the area of ISMS, Digital Forensic, Cloud Security, and Reliability Engineering. Also, he is the STQC's M-Plan faculty for ISMS, CISP, STQC, CIISA, CRP, and Cloud Security, and other professional courses. He has developed various reliability and software testing tools for our Indian industries. To his credit, he has completed numerous certification programs as well. On behalf of the organizing committee, I welcome you, sir, to chair the technical session 6 entitled Fuzzy and Digital System Reliability. Welcome you, sir.
Thank you, Mr. Velmurugan, for a very nice introduction. Actually, for this session, technical session 6, there were about 5 papers, A24, 25, 31, 35, and 58. Unfortunately, the other authors of the 4 papers have not turned up, so only Mr. Bhupati, that is A58, is available for presentation.
Yes, sir.
So my job has become easy. So, so Mr. Bhupati, so we have given you a slot of 10 minutes. Probably you can present your work in 10 minutes. Maybe another 5 minutes for to the dais to ask some questions. Go ahead.
evening to all. Myself Bhupati. So my presentation is fuzzy multivariate polynomial fitting and effective fabrication of fitting degrading Fe3O4 SiO2 SiO2 nanobag catalyst activity. So first I discuss the introduction part, fuzzy sets and basics, and the second part is fuzzy multivariate Lagrange interpolation and the fitting of multivariate polynomial under fuzziness using triangular fuzzy number, and the third part is fuzzy multivariate discrete methods and the fitting of multivariate polynomial based on triangular fuzzy number and a case study. So in case study we discuss objective of the study and the fitting of multivariate polynomials and the validation of multivariate polynomials, and finally I give conclusion and future also. So first I give basic definitions. Let X be an universe of discourse and A is a subset of X. We define the membership function, that is a graded membership function mu A of X equal to X to 0 to 1. Okay, and define the fuzzy set. So X and mu A of X, it's an ordered pair such that X belongs to X. So mu A is a membership function which belongs to 0 to 1. Next I define triangular fuzzy number. So we assume three numbers A, B, C, that is a real number A less than B less than C, such that the membership function for triangular fuzzy number is given by X minus A by B minus C, that is A to B, X lies between A to B. If X equal to B means 1 and B to C means we define C minus X by C minus B. Okay. Otherwise 0. Okay. We define the triangular fuzzy number, that is A bar, A tilde, that is a tilde, that is a fuzzy set which is equal to lower value, middle value, right value, that is AL, AM, A right, that is AR. So some basic operations of fuzzy set is addition, subtraction, multiplication, and division. So we take any two fuzzy numbers, that is A, B, C, A1, A2, A3 format plus B1, B2, B3. So we add two fuzzy sets, A1 plus B1, A2 plus B2 plus A3 plus B3. That is a left value, middle value, right value. Similarly for subtraction, so when we do A minus B1, A minus B means A left value minus B left value, A middle value, B middle value, A right value, B right value. Similarly for multiplication, we use minimum operation. We take a product of these two fuzzy sets. So we write minimum operation, next middle value A to B to, and maximum operation, and that is all combinations. Next to A division B, that is a division of two fuzzy numbers. We also write as per multiplication, we can use division operation. Next one, alpha cut set. So for any alpha value belongs to 0 to 1, we define the alpha cut set A alpha equal to X such that X belongs to X, such that mu A of X greater than or equal to alpha, that is a level set. Okay. Next, alpha cut set for triangular fuzzy number, we write A alpha equal to left value and right value, that is confidence interval. Okay. So A plus alpha into B minus C plus C minus alpha into C minus B. Next, crisp relation between dependent and independent variables. So I'm using multivariate polynomial for fitting of multivariate polynomial. I need to know what is an independent variable and what is a dependent variable. Okay. So multivariate variable means because more than one independent variable. Okay. And a dependent variable also more than one more than one variable. So X is a collection of independent variable, that is X1 to Xm, and Y is a collection of dependent variables, that is Y1 to Ym. So we write the functional relationship Ya equal to f of xi is a multivariate polynomial. Next, each vector in multivariate vector represented by more than one independent variable, that is xij for every I equal to 1 and j equal to 1 m. Next, with the crisp relation can be converted into fuzzy relation. We write the fuzzy set x bar equal to, that is a collection of variables, left value, middle value, right value. So left value can be written as, that is a collection of vectors. Each vector is a multivariate form. Therefore, we write x equal to xijl, xijm, xijr. Similarly, we write a fuzzy set x m, that is each vector in multivariate form. So we write the general format xijl, xijm, and xijr. This is the relationship between different variable and independent variable in fuzzy form. So I have used a triangular fuzzy number. Next one. So to fit a multivariate polynomial, I am using Lagrange's interpolation. Okay. So Lagrange's interpolation for multivariate polynomial. So we have a functional relationship, so that is y equal to f of x. Y is nothing but dependent variable, that is I will call it as f, f of x1, x2, etc. x1. So we write fuzzy set f of x1, f of x2, etc. f of x1. So next the function value and each x1, x2, x3, etc. xn denotes independent variables. So it is nothing but a multivariate, more than one independent form, that is multivariate vector. So now next we define fuzzy multivariate Lagrange interpolation. The equation is of the form f equal to summation alpha ei power l, sorry, not power, alpha ei left value, alpha ei middle value, alpha ei right value, that is xl ej, xm ej, and xor ej, that is 1 less than or equal to I, less than or equal to rho. This is multivariate vector form in fuzzy representation. So left value, middle value, right value, that is a triangular fuzzy number I am using. Next, alpha ei denotes the coefficient of this polynomial. So we need to determine the coefficient of polynomial using Lagrange interpolation. Next, the polynomial L of x, that is a polynomial representation, summation I to rho, and fi into Li of x. So Li is nothing, Li of x is a fuzzy set, which can be written as Li of xi equal to 1 if j is equal to I, Lj of xi equal to 0 if j is not equal to I. This is a usual Lagrange interpolation definition. I can convert it into a fuzzy representation. So in this case, for a triangular case, I am writing Lj of x equal to Lj of x left value, middle value, right value. So in this case, we need to find the coefficient of the polynomial. So the matrix will be non-singular. Each row in this matrix is a coefficient of the polynomial. Therefore, the matrix must be non-singular. Then only we can able to find the value of the polynomial. So determinant must be non-singular. Therefore, determinant of m that's a matrix, fuzzy matrix. This is equal to determinant of m left value, middle value, right value, all are not equal to 0. And general representation for a m left value, I am writing in multivariate form. Next, middle value I am writing in this form, and a right value also writing in matrix form. So in this case, let determinant of the matrix is non-singular. Therefore, I take this representation delta, fuzzy delta, that is a non-singular matrix. So Lg of x equal to del I of x bar divided by del I of del. And del I of x fuzzy set equal to, I write a left value, middle value, right value, triangular fuzzy number I am using. So left, middle, right. So similarly, del of x equal to del left value, middle value, right value. Therefore, based on that, I am writing a fuzzy multivariate Lagrange interpolation polynomial is equal to f polynomial, that is a lower prediction, is equal to summation I equal to 1 to rho. Fi is the functional value, fuzzy functional value for lower prediction into del I of x L divided by del. Similarly, for middle value and a right value prediction. So finally, I have to write the fuzzy polynomial prediction, which is depends on left value, middle value, and the right value. Some cases, if the sample, if this matrix M is a singular case, we can use the method is fails. Such a case, we are going to use method of least square. So method of fuzzy multivariate least square I am using. So for I am taking second order polynomial with respect to 3 variables only I discussed here. So multivariate polynomial I am using triangular fuzzy number. So to minimize the error, this is the polynomial representation. Sorry, this is a error prediction. So summation I equal to 1 to k del I square equal to summation I equal to 1 to k fi minus yp fuzzy set power 2. Okay, that is a square prediction. So fi is nothing but actual value, yp is nothing but the estimated value. So we have to compute the error difference between these two values. So the general multivariate polynomial for second order over 3 independent variable, I have to written like this. So y prediction, that is a polynomial representation, that is left value, middle value, right value, is equal to a naught a fuzzy set a naught a1 x, a2y, a3 z, a4 xy, a5 yz, and a6 x z, a7 x square, a8 ay square, and a9 z square. So this is the second order polynomial representation for 3 variables. So A0 to AN in all are fuzzy sets. I have to taken all fuzzy sets are a triangular format. This is a multivariate case under fuzziness. Therefore, herein we differentiate this function, this polynomial with respect to A0, A1, etc. ANI. We get this equation in matrix form. So matrix form, I got written like this. Multivariate case, left hand side is differentiate with respect to A0 to A9. I will be getting this matrix equation after I am writing in matrix form AX equal to B general format. Okay. So yeah, we need to estimate what is A0 to A9. That is our objective. So right hand side is function values given. So this is nothing but a water-Modi equations. Therefore, I am writing Water-Modi matrix star fuzzy coefficients equal to y bar.
Okay, Bhupati, I think you can conclude now. So go to the.
Okay, sir. I finished. So Water-Modi matrix. So just I am taking pre-multiplying. Finally I will be getting polynomial coefficients. So it is equal to Water-Modi matrix and transpose VAN inverse in star VAN transpose into y bar. Okay. So I will be getting the polynomial coefficients. So this is a fuzzy polynomial representation. So I got to estimate A0 to A9, lower prediction, middle prediction, and right value prediction also. Okay. So using these 3 predictions, I have to represent a multivariate polynomial under fuzziness. Okay. So case study in chemical engineering, I will be discussing. So the objective of the case study is and fitting of multivariate polynomial using mathematical methods and statistical validation and comparative study will be performed. Okay. So the case study is one factor at a time. Actually, it is a chemical engineering case study. There are 3 independent variables and 1 dependent variables involved here. So 3 type of independent variables: pH value, pectinous loading, and the temperature. And the different variables, we have to maximize finding maximal value for this nano biocatalyst activity. Okay. So 3 independent variables: pH value 4 to 9, 4 to 6, and pectinous loading 200 to 300 milligram, and the temperature is 0 to 8 degrees Celsius. Okay. Based on this independent variable, I have to maximize this maximal activity. I need to estimate maximal activity. So this problem I can solve it using fuzzy representation. Okay. So this is the fuzzy prediction. So drift data is 3 independent variable and different variables 1 maximal activity. And the fuzzy data set is I have to take 4 to 4.5 low prediction, 4.5 to 5.5 is medium, and 5.5 to 6 is high prediction I taken. So PL value 200 to 300 milligrams. So I got to take 200 to 240 is low, and 240 to 260 medium, and 260 to 300 high prediction. Similarly, temperature also I am taking. For maximal activity, 48 to 52 low, and 50 to 56 medium, and 50 to 6 to 60 very high prediction. So now next step, I have to defuzzify using average method. I will be getting the results, but I am not discussing results. I am not giving this results here. So finally, I will be getting maximum activity fuzzy prediction, and validation using chi-square distribution will be performed, and the chi-square prediction will give significant results also. So actually, results are not shown here. Full paper I will submit as early as possible.
Okay.
Thank you.
Any questions from the audience? Audience want to ask any questions?
Only one question.
Yeah. Yes.
You see, you lost in the last slide. You said that you want to see the goodness of it, of a fuzzy set, using the chi-square test, perhaps. Is that what you wanted to do?
Chi-square distribution I will be used to validate the results. So lower prediction, middle prediction, right prediction. These 3 values compared to actual values.
Yeah, fine. But in the fuzzy set operations, is it allowed to use the chi-square test to check the goodness of it? Because you are trying to talk in a different space altogether. And the operations algebra of fuzzy sets is a bit different from those of the probabilistic probability theory. Because you are working in norm space in probability theory, where you have, normalized measure. Whereas in the case of fuzzy sets, you don't have that kind of normalization that takes place. That is the flexibility that the fuzzy sets provide. And can we use the chi-square as a norm for comparing the distribution in the fuzzy set theory? I don't know. I'm just
Sir,
asking. I'm not an expert.
No, sir. Variations of chi-square distribution in the fuzzy set environment exist, sir. They are already defined.
Okay.
So we are planning to apply it. Yes,
Okay.
yes.
Okay.
She's the author of. Okay, she's the same Sujata. Okay. I could see almost all the 4 papers. She's author.
Sorry, sir. Like the students, they didn't even share the PPT. At least I could have done it.
And that's okay. That's fine.
Sorry, very sorry for
Actually,
that.
I have a question too. Actually, I'm not expert in this chemical engineering, but because of fuzzy logic, I just wanted to ask you a question. You had an assumption of having a triangular fuzzy number, right? What is why that you have taken that choice? Why not a convex or a normal? Was it an assumption that you have gone with the triangularization method, or you have not tried out the convex or normal or non-convex? Maybe, okay, you can look into it. So, see, everyone goes for the diagonalization method. I don't know, maybe they should try about the other methods also. That's my input to this paper. Otherwise, it's a very good, it's totally a mathematical, very good paper, very good presentation. Thank you so much. So, what about the other papers? Madam, you will be presenting something, right? Or you are the author for other papers too.
I think we can go to the other papers.
Yeah.
The other session.
Yeah, we can. Acha, one paper, then okay, we can move to the
other section.
Section 5. Yes. Thank you. Thank you so much.
Thank you.
Okay, thank you. Thank you, Dr. Velmurugan. Thank you, sir. Shall we go to the next paper in the main room?
Author for A34 is available, sir.
A34 author, okay. Yes, Madhumita. Author is available?
Sir, this is Dr. Umarani here to present for the paper ID A34.
A34, Umarani. Okay. Okay, madam. So welcome to this National Conference on Reliability and Safety. And I think you will have around 10 minutes to present your paper. So please proceed, madam.
Yes, sir. Thank you, sir. Sir, my screen is visible?
Yes, yes, your screen is visible, madam. Yes, proceed.
Yes, sir. So very good evening to one and all present here. So the title of my paper is Prediction of Reliability for Photovoltaic Quasi-Impedance Source Inverter. So I'm Dr. Umarani from the Department of EEE SSN College of Engineering, and my co-authors are S. Madhumita and R. Sudiksha, final year UG students, and Dr. R. Seirai, professor from the Department of EEE SSN, and Dr. Sujata ma'am from SNU University. So the content goes in this order, starting from the introduction, objectives, block diagram, the proposed model, its design and simulation work, followed by its results and discussions along with the references. So to introduce about the work, I have made an attempt to predict the reliability of the photovoltaic quasi-Z source inverter. So a photovoltaic module is generally used to convert solar radiation into electrical energy, but we can see fluctuating nature in both the radiation as well as temperature. So there is a necessity to develop a reliable interface between this PV module and the load. So the power conditioning unit is generally used in between. So that is going to be the quasi-Z source inverter in my case. So generally the PV system as a whole comprises of the PV panel followed by the power conditioning unit, which is nothing but the quasi-Z source inverter, and then it is followed by the load. So we have various electrical components like switches, either MOSFETs or IGBTs, inductors, capacitors, etc. in the quasi-Z source inverter. So reliability assessment is very important in very sensitive applications. So I have to go for an efficient model to predict its failure rate so that I can determine the reliability of the system. So this paper we have focused on binary decision diagram based model, which is deduced from fault tree to determine what will be the probability of failure for the proposed system. And I have compared it with the part count model, which is a traditional model, and I have compared the results. So what is single phase quasi Z-source inverter? Inverter is an instrument which is generally used to convert DC to AC. So this DC is applied from a PV source. So the main advantage of going for this quasi Z-source inverter is straight away I can go without a boost converter in between. So the conventional systems will have a DC-DC converter followed by an AC inverter, and then it will be fed to the load. But for the proposed case, the quasi Z-source inverter will just it will not require this DC-DC converter in between to boost the solar input. So this is the circuit diagram wherein I have a DC source followed by an impedance network and then a H bridge. A H bridge comprises of 4 switches, which is made of IGBTs, and the impedance network is made of various elements like inductors, capacitors, and diodes. So these are the different operating states of the quasi Z-source inverter. One is shoot through state, the other one is non-shoot through state. So during the shoot through state, I intentionally will make the switches in the same leg to simultaneously conduct. So the intentional introduction of the short circuit across the source is going to boost my input voltage. So this is not possible in the normal inverters. So by making advantage of this short circuit, I'm going to boost the input voltage, as well as during the non-shoot through state, I'm going to convert the DC which is boosted into AC, and it will be finally fed into the load. So these are some of the advantages of the quasi Z-source inverter. And these are the design parameters that I have taken for the proposed inverter. So I have taken a PV input voltage of 30.5 volt with a boost factor of 2. I operated with a frequency of 5 kilohertz. So the shoot through duty ratio is also provided here. So what is this shoot through? So in general case for applying pulses to the inverter switches, I will be comparing a reference sinusoidal wave with a triangular wave, and the pulses will be applied to the switches in certain sequence. But I have to convert some of the zero states into shoot through states. So I will be comparing the carrier wave with the DC line. So the train of pulses, which is shown in the second plot, will be added with the conventional PWM pulses. So wherever the switch should operate at zero state will be turned as on state. So intentionally I'm making my switch to conduct simultaneously in the same leg itself. So this is the output voltage which I have taken from the PSIM. So I have simulated it, and I have got this result of 61 volt, which is the peak voltage. So coming to the reliability part, as I have already mentioned, for sensitive applications, I need to estimate what is the reliability. So as we know the definition, so it is the, what is the probability that the system will perform its function without failure for a certain period of time under the given conditions. So some of the reliability objectives I have specified here. So the main objective is to prevent the occurrence of failures by predicting it priorly, putting into an application, a sensitive application. So we need to analyze through certain reliability models. So for the PV system, so the PV system has majorly 2 units, solar modules and the power conditioning units. So efficiency, modularity, and reliability, these are the 3 important aspects of any inverter. So the modularity and efficiency, both are based on the structure of the inverter or the topology of the inverter and how we are applying the pulses to the devices. But the reliability, which is the third component, is very important because the different elements which are used in the inverter will contribute to failure of the entire system. Maybe the connectors or the wirings, the array configurations, the charge controllers, inverters, anything can contribute to the failure of the entire system. So I need to identify what is the reliability. So I have gone for binary decision diagram, which is derived from a fault tree. So binary decision diagram is one of the mathematical model to find out what could be the reliability, what could be the failure rate. It is just used to predict what could be the failure rate of a particular system. So I have to go for minimal cut sets so that what minimum failure that can happen, which can lead to failure of the entire system. So for that, I have to first start with the fault tree. So for fault tree, I need to use the logical relations between the basic failure of certain events. So I have to find out what will be the contribution towards the top event failure. So I have to split the entire system into various subsystems, and each of these subsystems will have various basic events. So I need to fix what are the factors that will contribute to the failure of the basic events, and how these basic events will contribute to the failure of the subsystems, and how the subsystem is going to contribute to the failure of the main system. So my PV quasi Z source inverter is the top event. Its failure is based on PV module as well as inverter. When I talk about PV module, even we have the solar arrays as well as charge controllers. The solar solar module manufacturer themselves will give a warranty of 20 years. So coming to the inverter part, I have the quasi Z source inverters, impedance network as well as H bridge. So the impedance network comprises of inductors, capacitors and the diodes, and the H bridge comprises of the switches, MOSFETs, the semiconductor devices. So among all these basic events, the failure of the inductors or the capacitors, the diodes or the MOSFETs will contribute to the failure of the H bridge and the impedance network. So any one of the failure in these two systems will contribute to the failure of the inverter, and finally the PV based quasi Z source inverter is going to fail.
Sorry to interrupt, madam. Actually, we are running short of time.
Yes, sir.
But be quick, or I think the conclusion you can tell about, madam.
Yes, sir. Yes, sir. I'll just take 2 minutes of time to complete.
Sorry,
Thank you. No problem, sir. So this is the binary decision diagram that we have constructed. So X1, X2 to X11. So these are all the various states of the binary decision diagram that we have deduced from the fault tree. So for each of these notations, I have listed what are the events. So X1, X2, etc. up to X11. And this is the Boolean equation that I have deduced from the shown BDD. So what are the factors that will contribute to the failure of the basic systems? So with this, I have analyzed that the failure rate is 2.08 for every 10 power 6 hours. So comparing it with the part count model. So part count model is a very basic model. So we have taken the database from the military handbook 217. And these are the various factors with which we have computed the failure rate of inductor, capacitor and diode MOSFET. And finally, for the entire system, we have computed, and it is found to be 4.4928 failures for every 10 power 6 hours. So we have developed a hardware for the PV quasi Z source inverter, and we have generated the pulses using MATLAB Xilinx interface. This is the pulse pattern that we observed in the DSO, and this is the final output voltage. So in the hardware, we were able to obtain the exact output voltage. So the conclusion of my presentation is, so an emphasis is given on the reliability estimation of the quasi Z source inverter fed by PV, and I have compared the results of part count model as well as the binary decision diagram, and further investigations have to be done based on the hardware model.
Yeah, thank you, madam. Thank you. Very
sir.
nice presentation. So
Thank you, sir.
I think, it's a new idea to integrate the FTA concepts with basically the hardware. Already you have attempted a hardware, and still you go with the design technique FTA, and I think a very nice conclusion you have arrived at. So now I think if 1 or 2 minutes we can take the participants' time for questions. So I think Dr. Umarani will be pleased to answer. Participants, please. Anybody wish to ask some questions or clarifications on the work done by Dr. Umarani and team? Somebody is coming online? Yes. Yes, please. I think we are not able to hear, sir. Your audio is not very clear. Can you put a chat message?
Actually, Dr. Muthukumar, sir.
Yes, sir.
I think we are running short of time now.
Yes, sir. Yes, sir. Okay.
Yeah.
So
they can always send the questions by Gmail.
Yeah. I think questions can be sent through mail, and they'll be pleased to answer. Thank you. Thank you, madam, for the nice presentation.
Thank you, sir.
Thank you. Can we go to the next presenter? Next presenter is available.
Yes, sir.
Yoga Lakshmi and Balaji Rao. Yeah, sir. Okay. Presenter is available. Yoga
Yes,
Lakshmi.
sir. Yes, sir. Hello, am I audible?
Yes, madam. You can come online and you can start your presentation.
Yeah, is my slides visible?
Yeah, it's visible. It's visible. It is not in slideshow mode. Now it is.
Yeah.
Thank you. So welcome to the National Conference on Reliability and Safety, madam. You please press.
Thank you, sir. A very good evening to the respected chairperson and all the others gathered today. It's my pleasure in presenting my work in 5th National Conference on Reliability and Safety.
Madam, sorry to interrupt. Actually, please be quick in your presentation.
Yeah, sure. I'm Yogalakshmi and I'm a research associate at CSIR Structural Engineering Research Center. And this work is co-authored by Dr. K. Balaji Rao, who's my PhD thesis supervisor. So moving on, as we can see from the title, the work addresses service life prediction of reinforced concrete structures, which are subjected to chloride-induced corrosion. From the figure to the left, we can see that nearly 33% cause of deterioration in reinforced concrete structure is because of corrosion due to external fluorides. And in such a case, what happens is that chloride-induced initiation time becomes the service life because the corrosion propagation time is relatively small. And the right figure shows the corrosivity map of India, where we can see that India has a long coastline of approximately around 7,000 kilometers. And India being a temperate, a tropical country with the high temperature and high humidity, chloride-induced corrosion becomes a major problem that needs to be addressed. So for estimating corrosion initiation time, we need to first model the process of chloride ingress into the concrete cover. Most designers or engineers assume that diffusion is the primary transport mechanism in concrete because the convection zone in the concrete cover is relatively small, and hence there are lot of literature, lot of studies available in literature which is based on which are diffusion models, and these models are based on fixed second law. However, such models has some limitations. It assumes that the concrete material is homogeneous, and also it assumes a constant diffusion coefficient. However, with years, this limitation has been slowly addressed. So now time dependency of diffusion coefficient as well as time dependency of surface chloride concentration is taken into account. And for considering the heterogeneity of the material,
Madam, if you have sorry to interrupt yes. Actually. If you have the case study, you can go directly to the case study, madam.
Yeah. So in this work, we have in this presentation, I have proposed subdiffusion model for modeling the chloride ingress into concrete cover. There are a lot of experimental studies available in literature that shows that the pore structure of concrete is fractal in nature. Fractals are nothing but self-similar pattern that keeps reoccurring at different scales. So Janet explained the process of diffusion of ions through such fractal space by the process called subdiffusion process. So we can see a beaker where the ink dispersion can be seen. So this is nothing but a normal diffusion problem where the mean square displacement is directly proportional to the time. However, in our case, which is subdiffusion problem, the path becomes tortuous because of the fractal nature. Therefore, the rate of diffusion is relatively small compared to the normal diffusion. Therefore, the mean square displacement is directly proportional to the time to the power of alpha, where alpha ranges between 0 and 1. So unfortunately we don't have analytical solution for this fractional time partial differential equation. So we have adopted a numerical solution. So this solution is based on finite difference method. This solution is conditionally stable. This is a limitation of this solution. It is conditionally stable. However, the fractional operator that is involved in this equation plays a very major role in modeling. So as we can see from the figure, the green line is the normal diffusion, which is also the Brownian motion. So a Riemann and Livoli operator, fractional operator, models a process as a subdiffusion process, as you can see from the blue line at larger times. However, a Capito derivative operator, which is previously which is used in the literature, it models a process as a confined diffusion process. Therefore, in this present work, we have modeled the process by using Riemann and Livoli operator, and the initial condition is considered as a Dirac delta function, and the boundary conditions at the source end is nothing but the surface chloride concentration, and on the other end, the derivative of concentration is assumed to be 0. There are 3 parameters involved in the solution. One is surface chloride concentration, CS, alpha, which is the exponent, and D alpha, which is the diffusion coefficient. So these 3 parameters in the solution.
Please conclude, madam. No, I think it's time.
Okay. So these parameters are fitted fitted in MATLAB using seen as an optimization problem, and MATLAB is used. So a least square, the objective function is nothing but the least square error. So here in this slide, a comparison is made where the proposed model is compared with the FIB service life model, which is based on Fick's law. So we can see that near the level of reinforcement, actually the previous year chloride profiles are used to estimate the model parameters, and the latest chloride profile is predicted using the estimated model parameters. So from the figure, we can see that both the models perform relatively well near the level of reinforcement. However, even a small it can be expected that even a small difference in the chloride concentration may result in a significant difference in the corrosion initiation time. So next we are moving to corrosion initiation time. By from the numerical solution, we'll be getting a matrix whose elements contain the values of chloride concentrations. So the rows in the matrix represents the location, and the columns in the matrix represent the time. So by scanning the row that corresponds to the location of reinforcement, we can calculate what is the corrosion initiation time. So this is how corrosion initiation time is predicted. So the results are also validated. So for this purpose, 2 case studies from the literature has been taken. These are real structures. These are jetty piles. One is jetty pile and one is jetty deck. So the model is validated using these 2 cases, and we can see that the corrosion initiation time in case of Liam is around 34 years, and also Liam in his paper he proposed the initiation time to be 35 years, and also in case of Michael data, the corrosion initiation time is around 56 years, and the time at which the paper was written, that is the age of the structure was 54, and at that time there was no delamination found. So these are the observations made, and so far we have dealt with the deterministic value of corrosion initiation time. So now now we go into probabilistic analysis.
I think time is up. Please conclude, madam. Come to the conclusion.
Yeah.
Okay, Yoga, you can conclude, Yoga. Come to the summary.
Okay, so previously there are a couple of literature that has used the application of subdiffusion model for modeling the chloride ingress into concrete. However, in the present work, for the first time we have seen that we have related the fractal nature of pore structure to the fractional exponent of the fractional differential equation. This is the new thing that we have done here, and also here for the first time we have studied the importance of fractional differential operators for modeling the chloride ingress. And I would like to conclude that such a model is less conservative than all the other than the FIB model, and also therefore it may result in a more economical section. Yeah, thank you.
Thank you, madam, for the nice presentation.
Yeah.
Yeah, we can take one question from the participants. Otherwise, I think you should be available to answer your queries over mail. Any questions from the participant side? Yeah, okay. Thank you, madam. Thank you very much for the nice presentation.
Thank you, sir.
Thank you. You can log out. So to summarize this session, I think we had the presentation of about 4 papers from this panel and 1 paper from the FUSSY panel. I think both of us are available, myself and Dr. Velmurugan. Actually, the first two papers and the last presentation was on the predicting the service life, and one paper was on the photovoltaic quasi-impedance source inverter reliability prediction. I think she has followed the Milan book Farskone method, and actually she has improved the efficiency of the impedance source inverter by switching on or shunting during the zeroth state. So thereby she's achieving high voltage output. So I think all good work the presenters have done, and they made a nice presentation also. I think I won't reserve any time for questions from the audience because already it is too late. Thank you very much. Dr. Velmurugan, you can also sum up the paper on fuzzy.
Yeah, so only one paper was presented. Of course, the paper was very nice. Maybe you can think of adopting the methodology there, fuzzy methodology. Restricting only to triangle may not be so maybe there is a scope for improvement to look at the convex model, normal model, and other things. Okay, this otherwise the paper is very good. Thank you so much.
Thank you very much. Wish you all the best for to all the participants.
Also wish everyone. Thank you so much.
Thank you.
Thank you, Muthukumar sir and Velmurugan sir for chairing our session. So next we have a brief presentation by Rahul Abargal from RELSEV, who are the platinum sponsors for this event. So based on the request, I am pausing the recording as well as I am stopping the live streaming. Over to you, Rahul.